Can you introduce yourself? Who are you?
I'm Max Sherman, PhD in physics, a professor at the University of Nottingham in the UK, and otherwise retired and a consultant.
And you're also involved in ASHRAE, I believe?
Yes, I'm quite involved. I do a lot of volunteer work for ASHRAE. I'm currently on the Environmental Health Committee and currently a member of ASHRAE Standard 241. I'm the vice chair.
Can you provide a brief overview of your career? What motivates you to continue the work in the area that you specialize in?
I started off in graduate school in physics at Berkeley, and I was attracted to working in this area because my eventual advisor, Art Rosenfeld, said that in the energy crisis, which was happening, this was the mid to late 70s, the engineers needed help and the physicists were the people to do it because something disruptive was happening and things had to change. So I began looking at energy, as one did back in the late 70s, and in particular, airtightness and airflow in buildings. And I realized, firstly, that there was a lot of energy to be saved, and we began doing that. But then I realized as we did that, homes were going to become tighter and not well ventilated, and that was going to be a different kind of problem, as air quality itself would become a problem that people had to address. And so I began working on that side in the late 80s and have been going from ventilation to air quality to health since then.
There are three major ASHRAE initiatives that you've been involved in that are related to the residential market. Can you explain what those initiatives were and their impact?
The reason I got involved in residential in the first place was because I was looking at airtightness of the envelope, and envelopes matter in small buildings like homes. They don't matter as much for ventilation in terms of large commercial buildings. A lot of what I did was focused on residential. ASHRAE's always had an indoor air quality standard. Standard 62 is ventilation and indoor air quality. But in the 80s and 90s, it did all buildings. And then I realized, several of us realized, that homes were different than commercial buildings, and there were different rules and different things that happened. So it was necessary to have a standard that looked at them separately from other kinds of buildings. So ASHRAE Standard 62.2, residential ventilation and indoor air quality, was created around the turn of the century, and I was its first chair. So in 2003, ASHRAE had its first residential ventilation indoor air quality standard that I chaired. That was perhaps the first thing that I did. The second thing was, in the years to come, I realized that there's as much energy in the residential sector as in all the rest of the building sector together, roughly. And yet ASHRAE didn't handle residential as much. Most of its concerns were commercial. I made my case to the powers that be, and eventually, after doing some ad hoc committee work, ASHRAE created a residential buildings committee to coordinate all the residential building aspects. And I was its first chair. So that committee is still going on. They're still being productive. They coordinate the various residential aspects of ASHRAE and highlight what needs to be highlighted. Then the third thing was probably having to do with COVID. ASHRAE was very good at responding to COVID. ASHRAE was one of the first organizations to recognize that COVID-19 was airborne transmitted and that infectious aerosols were going to be the key thing. We recognized that before the CDC and the World Health Organization admitted it anyway. ASHRAE created the Epidemic Task Force. I was one of the roughly dozen people on the Epidemic Task Force, which was chaired by presidential member Bill Bonfleth. We broke up into a whole bunch of working groups, teams, to each one to handle different aspects. And I was chair of the residential team. And that team brought together all the aspects of residential. And if you look on the COVID-19 site, which is still on the ASHRAE website, you see a lot of recommendations, and those were recommendations that my team generated. That activity turned into what is now Standard 241, and Bill Bonfleth asked me to be vice chair based presumably on what I did on ETF, and that's how we got to where we are today.
Yeah, the task force was like the emergency response to the situation. It was a community involvement from so many different parties, and then 241 was a translation of all of that work into a standard.
The ETF was the house is on fire. Where should we throw the water? And people did what they could, and it wasn't a standard. It was guidelines, and some could be done, some couldn't be. But now that things have settled down a bit, we need a more structured, organized response to infectious aerosols in general. And that's why 241 is a standard, not just a bunch of recommendations. And it's not specific to COVID-19. It's for any infectious aerosol, but it would have been useful for COVID-19.
What's the typical timeline for a standard from ASHRAE to go from inception to publication?
Oh, 5 years is a typical number for a new standard. ASHRAE process is very slow and deliberate in general when trying to make standards.
And 241 was how many months?
4 months. It was, yes, it was a crash program. The White House asked ASHRAE to put something together very quickly. They wanted a standard that could be referenced, that people could start using right away. And we're not happy with the standard ASHRAE timeline and asked the ASHRAE Board of Directors if they could make something happen. And the board decided that it would.
Amazing. So that process, I'm really interested in peeking behind the curtain. What kind of turbulence was there to coordinate the people required to make this happen in such a short timeline?
Less than you might think.
Huh.
The board debated whether to do this or not, and then decided, okay, we're going to do this. And we're going to supply the project committee with whatever tools and resources it needs to get it done. So they asked Bill Monfleth to chair it, and he asked me to vice chair it. And what essentially Bill and I did was what people think of as the Tiger Team approach, which is famous from Apollo 13. The idea being that failure is not an option, that it will get done. Now the question is, what does it take to do it? The first thing is that we had to waive a bunch of requirements that ASHRAE has for any normal standard. In particular, almost all ASHRAE standards are also ANSI standards. ANSI has certain requirements to do it. ASHRAE isn't required to do that for an ASHRAE standard, but it always does. But in this case, it didn't, because to follow the ANSI process would take too long. So the idea was, first we'll create a standard, and then after it's out, we'll go back and slowly start the proper ANSI process to do it. So that allowed us to have a shorter time frame, but we still had to have a product that worked. And the approach that Bill and I used was to find enough high quality people. ASHRAE is full of really top-notch people, and we had to find them spread over all the areas of expertise that were necessary to make this happen, spread all over the interest groups that were going to be involved here. And all of them also had to have the failure is not an option mode in mind so that we could get it done. And there were between 100 and 200 people who ultimately applied to be on the committee. And Bill and I selected the ones that would meet all of those criteria, we hoped, and put it together. So there was plenty of, shall we say, small scale turbulence as things were being developed. But everyone knew that we had to reach consensus, that we had to get something done on a fixed time scale. People were willing to put aside perhaps some of their closely held beliefs if the rest of the people were just not willing to go along with it. And also compromises had to be made. Things aren't covered as well as we perhaps would have liked them to be, and will get covered in future versions, but there's a standard that's out there.
And you use the term consensus-based standard. Does that indicate that consensus is not usually the state of other standards during the process?
Well, no, consensus is required of all ASHRAE standards. It's a consensus-based approach, which means more than just a simple majority, but not necessarily everybody being on board. But a substantial majority have to be on board to get there. And also that implies the same thing for the reviewers in a normal ASHRAE standard. That is, the people who comment on it. Now, that's one of the things which we did not fully do in this version of the standard. The standard was put out for public review. We did get hundreds of comments. We read and thought about each one of the comments and then decided what we were going to do. Whether that pleased the commenter or not wasn't something we checked on. We didn't have time for that. In a proper consensus standard, all comments would be resolved, or a higher body would approve the fact that they weren't resolved.
Okay. That makes more sense. There's some of the process elements of ASHRAE standards creation that myself, as new to all this, is great to understand that. Now, can you explain or discuss the importance of indoor air quality and its impact on public health? Do you have any personal experiences that would drive your passion for improving indoor air quality?
Let's start off by saying that indoor air quality is usually considered a chronic issue, something that's you're in the air 90% of your life. And so it's something that affects you totally. Different from the 241 issue where you talk about infection, which is a short-term thing that happens once in a while or a pandemic that happens once in a lifetime. Those are acute issues, which you handle very differently. But indoor air quality is something that we have all the time, everywhere, and it's generally thought to be the fifth most significant health impact in people's lives. So it's really quite important. So understanding indoor air quality generally has been something I've been doing for decades, of trying to figure out what's important, what's not, how we can make it better, and how we can improve people's lives and people's health. And that involves understanding the interplay between health and contaminants that are in the indoor environment and ways to reduce those contaminants.
On that note, why is it so challenging to quantify the pollutants in our air? And what kind of technical advancements are needed to improve our ability to quantify or monitor our indoor air quality?
First of all, there are thousands, maybe hundreds of thousands of compounds in the indoor air, and some of which are harmful, most of which are not harmful at the levels that you see them. So identifying which ones are important is a thing. And remember, most of these things are in the range of parts per billion. That is, there's not very much of it in the indoor air. You and I, just sitting here today, are parts per billion of the US population. So that gives you some idea of how scarce these things that we're looking for are. Nevertheless, there are sensors that can measure these trace things, but they're not cheap. They're something that researchers can use, but not something that you could put in every home, generally speaking. So it's hard to know what you have without spending a lot of money doing research, which isn't something you normally want to do.
And maybe to expand on that, there's a difference between measuring the quantity of a class of pollutants in the air versus speciation. And so can you explain that difference?
Sure, that's huge. Just because you know how much of something there is doesn't mean you know how harmful it is. And different compounds can be millions of times, billions of times more harmful than other compounds. This is why there's a common kind of product often that goes by TVOC, total volatile organic compounds, where they'll tell you how much TVOC you have. This is a less than useless piece of information because TVOCs add up the amounts of sarin gas and ethanol with the same weighting. But guess what? You really don't want to have much sarin gas around you, but you can stand a lot of ethanol around you. What's worse is most of those sensors don't actually measure TVOCs at all. They measure some strange things that's been calibrated. A lot of these cheap sensors that tell you something about your home that you put in your dashboard, they call them dashboards, you can put in meters. They don't tell you anything useful at all. So people think they're getting useful information when the information is not terribly useful to the average person.
Can they be used to take some sort of action on the indoor environment?
Oh, of course they can be used to take action. It may not be the proper action, however, because it depends what's triggering them. If you only had one compound, like formaldehyde, and you could only measure that compound and you saw it went up, then you might be able to take reasonable action. But if you see your TVOC meter in your home go up, it could just be because somebody had a beer or because somebody cleaned the floor with floor wax or a zillion other things that are pretty much harmless to you. And it might not recall at all when you have something like acrolein. Acrolein is a compound that comes from burning wood or any such product incompletely. And it was a gas used in World War I as a chemical warfare. So it's a very bad thing for you. It hurts your eyes a lot. Very little of it is very bad. There normally isn't enough to matter, but no TVOC meter is going to alarm on that because there isn't enough to matter.
Interesting. Let's say all the wildfire smoke that we've had, that acrolein gas, that would have been one of the things affecting our health?
It could have been. It's a lacrimator. It makes your eyes water. If your eyes were watering, it could have been that. The wildfire stuff is mostly particulates when you get away from it. Obviously, right in it, there's all sorts of things. But over the larger scale, it's mostly particles that are the issue. And the particles have some SVOCs on them, which slowly emit smelly things, which is why you get that wildfire smell.
Back to taking action on our indoor air quality. I noticed that in ASHRAE 241, there is a little bit of guidance surrounding electronic air cleaning technologies like ionization or PCO. So normally ASHRAE hasn't taken a definitive position regarding these technologies. Can you explain why?
ASHRAE tries to avoid picking winners and losers. What ASHRAE wants to recommend is things that are safe and effective. And there are various ways to demonstrate that. Many products don't, so ASHRAE doesn't take a position on that sort of thing. But 241 actually is really good in this regard. And it's one of the major breakthroughs or game changers in 241 is that it lets you use any technology. You want to use a cosmic ray particle eliminator, that's just fine. You want to use a flux capacitor, that's just fine. What you need to do, though, is pass some tests. You have to show that it does what it's supposed to do in terms of eliminating. And you have to also show that it's safe if it's an active sort of thing, that it doesn't emit or cause contaminants of concern to happen. And ASHRAE has a backup test method in 241. It lists all the test methods that are out there, and it says if your technology meets one of these, then you're good. Otherwise, use this one to demonstrate safety and effectiveness.
With electronic air cleaners, though, going back to VOCs and how difficult it is to quantify what's actually in our air, I had recently written a piece about electronic air cleaners, and I equated that a lot of electronic air cleaners almost do like musical chairs with the particles and chemicals in the air. Like, you don't know what's going in, so it's going to be difficult to predict what's going out. And then you need some fairly advanced instrumentation to quantify what's coming out the other side. So are the test requirements in 241, does it make it accessible for that type of testing, or at least that alternative method that you're talking about?
It's accessible to the manufacturers of the equipment. It's not the kind of test you would do yourself at home. But the idea being that if you wanted to say you complied with 241, whatever technology you were using would have had to have documentation that they, in fact, did these tests and what the results were. And we had a group of air cleaning specialists who are very up on all this stuff. There's a section and an appendix, which is a test method on how to do all of this. And it's one of the big improvements of this standard. Hopefully, there will be standalone test methods for some of the technologies which don't yet exist. There's a couple that are right on the cusp of being approved, but aren't yet, but will be. And then there are others that need to be done. But the basic idea is you have to demonstrate that your technology is safe, and you have to have demonstrable effectiveness numbers to use in the standard.
I know for UV lights, there's 2 UL standards that a manufacturer can choose to test to demonstrate that their devices are safe and, let's say, are not emitting ozone. Are we going to have something like a UL standard that applies to other technologies like what we have today?
The UL standard that requires equipment to be ozone-free is UL 2998, and that's required of anything that's being used here. So we have that one. But for other kinds of technologies, for your soon-to-be invented flux capacitor technology, you're going to have to have You're going to have a standard to see what it might produce that would be bad for you. And that doesn't yet exist, but we have the bones of a generic one in there so that emerging technologies can be fairly rated.
Let's talk about automation. So the 241 standards, does it contain anything that relates to automating a building that could apply to BMS, BAS, or even simpler, let's say, thermostat or ventilation systems that could be found in a home?
There's no requirement for automation, but for any building, you're supposed to come up with a building readiness plan. And in that plan, it says, what are you going to do when the time comes to initiate the infection reduction management mode, where you're going to say, okay, I'm going to do this higher level of protection. And that can involve automation, but you have to describe what it is. And a home thermostat could easily fall under that. It could, you could imagine a switch that the manufacturer had that put it in the mode that gave you the right numbers to meet 241. So you have to describe it, but there's no exact requirement on what it has to be.
It allows a lot of flexibility in being able to achieve that outcome.
And that, in general, is the approach we took because we didn't have time to write every technology, every option, and every detail. So we stated what you had to achieve, and then in many cases we said, okay, just tell us how you're achieving this. Sometimes we could put in standards, sometimes we'd be specific, but a lot of times it had to be general. One particular residential example of that is we say you have to have a protected space in a residential environment, because we know that there's going to be infected people living at home, and you want to protect the uninfected people from doing that. So we say you have to have a protected space, but it's very general at the moment. It's one of the things that needs to be developed further in future versions of the standard. But the idea is clear, and you have to explain what you're doing in order to meet that.
There's another concept, you touched on it, equivalent clean airflow rates. I saw a lot of practitioners in the HVAC field excited about this new concept. So can you explain it, and how can it be applied to a residential home?
So ECA is basically a concept that allows you to add outdoor air ventilation, particle filtration, UV light, and flux capacitors all together in a way that tells you what's the equivalent amount of the infectious aerosol that you're getting. It gives a lot of flexibility. And that was the whole idea, that we didn't want to tell you how you had to do it. We wanted to give you full flexibility of doing it so that it makes sense in your climate to use lots more outdoor air, do that. If it makes sense to use particle filters, do that. If it makes sense to use UV, do that. And it all has to just add up to a certain number, which is specified for each occupancy in the standard. And that way, we're not picking winners and losers. We're just saying, get this done, whichever way makes the most sense in your design, in your situation.
I saw that there's an associated worksheet that goes along with 241. It's basically like an Excel file that is like a calculator for this. So is that something that you see HVAC contractors being able to use when designing systems?
It's not that complicated. There's no magic there. It's just a tool to aid you to make life easier, so that if you want to figure out, let's say you've already decided how much outdoor air and whether or not you're using UV, and now you want to know how much particle filtration you have to add, you can use this sort of thing, or vice versa. So yes, it's a tool to be used. And we imagine that the people who are going to help write guidelines for the actual installers and people in the field are going to use tools like that themselves and help people figure out how to do it.
Okay. And in our conversations leading up to this session here, you associated the term Infection Risk Management Mode, or IRMM, and ASHRAE's upcoming guidelines on wildfire smoke with the term Resiliency Standard. So what does that resiliency term mean for you?
As I mentioned before, there are things that are ordinary, like day-to-day indoor air quality. But then there are extraordinary events that happen. It can be a wildfire, it can be a pandemic, it can be a flu season, it can be a truck exploding, a pipeline exploding nearby, especially if you're Canadian. Those are extraordinary events, and you want to be resilient against extraordinary events. That means you want to be able to have the capacity to adapt to them, that you don't use much of the time at all, but it's there. We use resiliency when we talk about having a house protected against a certain kind of tornado, or by having a safe room, or being on stilts against a certain kind of flood. Here we're talking about HVAC things to make you resilient against events that affect the outdoor and therefore indoor air. Wildfires and epidemics are one of those sorts of things. So 241 is part of a resiliency package. That is, it's what you do to be resilient against infections. It's not something you're going to run all the time, necessarily anyway. It's something you're going to have in your back pocket to do when the time occurs.
Whether it's residential or commercial buildings, the goal would be to have building designers and operators to integrate this resiliency approach into their systems, so that when the time comes, when there is a wildfire smoke event or another epidemic, there isn't going to be a scramble to try to implement everything all at once, and they can just flip a switch.
That's the idea. Some things could be perhaps implemented the last minute, and that's what we tried to do with the Epidemic Task Force. But some things have to be built in and require some work ahead of time to be functional for you. And so 241 allows you to know what to do. It doesn't tell you when to turn it on, but it tells you what to do when you do turn it on.
Could it be equated to an insurance policy? You have it just in case there is going to be extreme measures?
You have it, and you hope never to use it, because you hope that there's never going to be an infectious situation. You hope there's never going to be a wildfire, a flood, or a tornado, but you have it there for when those things happen.
I'm just imagining that some contractors could position a 241 package like, hey, if you're sensitive, we'll design to these guidelines and we'll set up the automation. We'll follow the process so that it doesn't need to be turned on all the time. So you won't be suffering any of the additional, let's say, energy use from additional ventilation or filtration, but you have this whenever you need it, and we'll make sure that it works for you instead of having to scramble to put it in last minute.
If people care about it, if people want it, then I think there'll be a ready market for contractors. You could imagine a developer saying, I'm going to build this subdivision to be 241 compliant, and put a green star, like an Energy Star kind of label, to say, hey, I'm doing this. This is what you have to do when you want to turn it on. It's even perhaps more important in multifamily, because people want to be protected from their neighbors. And you could imagine that a apartment building owner could ask for more rent if he was a 241 compliant apartment building.
Amazing. I see a lot of good use cases in positioning it that way. Why do you think there's such a significant gap between there being better HVAC and IAQ policies and practices in the residential market versus in the commercial building market? And what steps can we take to bridge that gap?
I think it fundamentally comes from a man's home and is his castle kind of view. When you're in a commercial building, you're at the mercy of the building owner in terms of what you're exposed to. And if you get sick in somebody's building, that the building owner can become liable. They want to know that they have some protection in the legal sense by saying, we followed a certain standard. You can't blame us. We did the responsible thing. On the other hand, when you're in your own home, you don't want people telling you what to turn on and what to turn off. You don't want the ventilation police knocking on your door to check and see if your filters have been changed regularly. There are plenty of places that don't allow smoking, but we don't ban smoking in people's homes. There's a fundamental philosophical difference on what people are willing to do. And on the flip side, from an ASHRAE perspective, you don't tend to have professional engineers design the HVAC system of every home, whereas you do in every commercial building. So you don't have somebody who has an ethical obligation to follow a standard as a PE would have. You just have a guy who's installing the HVAC system. There are all sorts of different motivations here, and that's why it's a whole different ball of wax.
Yep, I've seen that in all my conversations too. Would you be able to explain the value or significance of the ASHRAE 241 standard to different audiences?
I think there's a couple of tiers of explaining, and those will vary. To the HVAC professional, that's who it's written for. This is instructions on how to do it, and the purpose and scope of the standard itself tell you what it's there for. It's there to provide risk reduction in the case of an infectious aerosol present. And I think everybody can understand what that means. It's there to protect you when there's some sort of epidemic going on. It could just be the flu season, right? It doesn't have to be COVID-19. You're having a bad flu season where lots of people are infected. You turn this on and give everybody some extra protection. And I think everybody can understand that. And then you say it's about giving enough clean air to each occupancy. And then there's a list of what that amount is for different occupancies. And I think pretty much everybody can understand at the basic level what that means. You give the equivalent of clean air, whether it's filtered air, outdoor air, or sanitized air, you provide that, and that dilutes the viral load. That just reduces the amount of stuff that's around to infect you. It doesn't get rid of anything. Nobody's pretending that make the risk zero, but it's substantially reducing the amount that you would have. The rest is a detail, and it depends on how much detail they want to go into, how you quantify the different aspects of clean air, what it takes you, and how you make sure you're not introducing any new risks when you do that. So that's the safety part of all those technologies. And then there's instructions on how you do the planning, the operations, the maintenance. Again, those get into details that the general public don't really care about, but perhaps would like to know that they're in there, whereas the designer, the operator, the maintainer, they want to know what needs to be done. In that way, it's layers, and those layers start at the easiest to understand.
For residential HVAC contractors that might want to implement some form of the 241 standard, could you provide any advice of how they could adopt it in single-family homes?
The easiest thing to do, the most cost-effective, the cheapest, is if you have a central air handling system, is to upgrade the particle filters, because pretty much every central air handling system can be programmed, or at least has an on switch that can run it continuously. And if you have the right filters, you've essentially met the airflow part of 241. The separation part of the residential 241 is something that you would have to fake at the time in an existing home. You could imagine building it into a new home, but at the moment, it's pretty loosey-goosey, so you might not want to do that in a retrofit environment. But if you're designing a new home, you could perhaps figure out how to do that more explicitly. Of course, in a radiant heated home, it's more expensive because you have to add air cleaners to the situation in order to meet it. So that could affect your design choices in your HVAC system. You could choose ones that are easier to comply with 241 than others. And I should add the 241 requires as a prerequisite that for homes you meet ASHRAE 62.2. So you have to have the basic IAQ protective development, a certain amount of outdoor air, range hoods, all the things that are in 62.2, in addition to the correct amount of ECA.
So ASHRAE 62.2 that's a great tangent or thing to talk about for a bit because of your involvement in that work. My own research in trying to figure out how ASHRAE 62.2 is being applied to the market, it seems like there's confounding variables that have made it difficult to be properly adopted across all of North America. You have municipalities that adopt varying different degrees of ICC standards. The mechanical code seems to be so different from city to city, from state to state. And in addition to that, a lot of HVAC contractors often are not trained or even understand that 62.2 exists. How do you see 62.2 having impacted the market so far, and what else can be done to be able to continue making it effective?
There are some large users of 62.2. There are many jurisdictions that require 62.2. The two largest users are the state of California, which has required essentially 62.2 for many years, and the Weatherization's Assistance Program of DOE. So does EPA's Indoor Air Quality Plus. So there's a variety of places that require it. But as you say, there's zillions of jurisdictions, and each one does codes differently. And it's up to them what they adopt. There's plenty of people who can train contractors and installers on what to do for 62.2. There are courses out there that are available, but there has to be the demand for people to want to do it. Because if they're not required to do it, it's going to add cost. And of course, then the builder doesn't want to add cost to the building if he doesn't have to. It's the motivations. If code requires it, or if there's a labeling program that's worth something, then people can do it. But otherwise, it's not going to happen. It can happen in the spec builder, in the spec area where the guy who's commissioning to build his home wants to have 62.2 and 241 and anything else in it. But the majority of homes aren't done that way. So it's going to depend on people asking for it or requiring it.
So it'll be a bit of time until we get there.
We think that COVID-19 was beneficial in that sense, in that it brought people's awareness to indoor air quality. And we're seeing more interest in doing better than before the pandemic.
Yeah, there's a term that I like to use, which is indoor air quality activated. When I was working at Haven, there'd be so many people that just wouldn't get it unless they have a family member or themselves are affected by asthma or COPD or another ailment that is life-changing. So unless you go through that activation experience, then yeah, people don't care.
That's right. Now, we're doing some research to try to show the benefit of indoor air quality in terms of your lifetime health outcomes. And that is scientifically useful, but doesn't speak emotionally to anybody who doesn't think about those sorts of things, isn't activated, as you say.
Is that related to the DALY and the QALY, like those scores that I've been seeing pop up?
DALY stands for Disability Adjusted Life Years. It is a metric that's used by the health and economists to try to figure out how much harm, let's say, you got into because you lost your leg in a car accident. How much is that worth? And that's where that whole concept came from. What we have done is apply it to indoor air by looking at how exposure to contaminants affects diseases and how those diseases then affect the rest of your life. And we can turn those into DALY numbers for indoor air quality. And that puts it in a whole different regime. It certainly helps quantify what's important and what's not. And it also helps to compare it to other things that may happen to you, other kinds of health effects, and for that matter, non-health effects.
When I was at Haven, I was trying to figure out how to help people see the value of solving their indoor air quality problems, and DALYs and QALYs. It seems like a fairly nascent research initiative, but I see that there could be a point in the future where our air quality monitors are just good enough. If every space is being monitored and you also have your outdoor air data, would it be possible to have individually calculated DALYs and QALYs for every person's personal experience?
It's possible to do that now. It's just very expensive because you need all these expensive sensors in order to get the numbers that you would go into that. And the DALY research is ongoing. It's an active area nationally and internationally in terms of a follow-up. It's well known in the research area. It's not yet down to the average person's thing, but it's quite interesting. For example, it shows that far and away, the biggest indoor contaminant to worry about is particles. Nothing else comes close to the DALY impact of particles in the typical environment of today.
What you're saying is that the particle sensors right now, unless you're doing speciation, you won't be able to calculate a partial DALY because knowing quantity of particles isn't enough to be able to do that calculation?
Quantity is enough for that calculation. You
Okay.
could do it, but my theory is that unless you're really geeky and want to know this stuff, the right answer is just put the particle filters in so you know you don't have very much. You don't really have to know what it is, just get rid of it. And the cheapest air cleaning there is particle filtration. It's easy, it's well known, it's low risk, it's inexpensive. This is, by the way, a side benefit of 241 in residential. If you could just have special filters to stick in during IRMM, but they're not that much more expensive than the regular filters. So you might as well just use those filters all the time. And then you're getting amazing particle reduction all the time and improving your IAQ.
And you're not introducing different resistances, let's say, so that the system always has that type of predictable static drop across the filter instead of mixing and matching with whatever's available at the time.
Static pressure is often the thing people talk about. Turns out it's not as big a problem as people actually think. Most of the time, that's a problem when the duct system wasn't designed well in the first place, and there's a lot of static pressure drop in the duct system itself. The difference between a low efficiency filter and a high efficiency filter in pressure drop doesn't have to be very much. It can, of course, push a bad system over the edge and make it fail, but it shouldn't. A minimally careful design would see that's not going to be an issue.
Just focus on good filtration. And if you install it right and everything's sealed, one of the other big things that HVAC contractors deal with all the time is dirty blower wheels and clogged drain pans because of the snot that grows. And so there's something that Jim Bergman talks about often, which is if you're using proper filtration, you'll never have a clogged drain pan and probably won't ever have a frozen coil unless you have an airflow problem, because you don't have all of that additional particulates that are building up on the equipment that are causing the microbial growth. Could it be said that if you have MERV 13 and you've sealed the filter slot and sealed the equipment, it is very improbable that you're going to end up with those additional problems?
One of the first studies we did along these lines back in the 90s was look at how particles build up on air conditioning coils. The person who did that, Jeff Siegel, who's now a professor in Toronto, he did the study and we're using campus equipment, and he doesn't like to say it this way, but I say that he found out that a typical residential coil was equivalent to a MERV 5 filter. It caught that much particles, which is why when we first had filtration requirements in 62.2, we put in a MERV 6 filter so that it would get most of the stuff before it hit the coil. Now that's since moved to a MERV 11 filter over the years, most recently, but that was the logic. Yes, you want to keep the motor clean, you want to keep the coils clean. All of those can become sources, all of those can cause problems. Putting in good filtration is a win almost all the time.
Lovely. That's the next article that I'm actually writing, is just all about filtration, and the guidance is really straightforward. It's just not enough people follow it.
You have to make sure that the duct system and fan can handle the little extra pressure drop, but then they won't have to handle the extra load of being gunked up by all the dirt. So
related to the future, then, the updates that the committee is going to be doing to the 241 standard, are you thinking of including additional or different guidance for single-family homes?
As I mentioned before, this was all done in a very short period of time, and there were some things that were not done in as much detail as we would have liked. And the residential part is one of those areas that needs more fleshing out. But in terms of how we're going to do it, there are a variety of different ways that we're looking at. First of all, this is a standard under continuous maintenance so that people can send in ideas, requests, additions. ASHRAE has a process for that. We also have a desire to turn this into an ANSI standard, which will require the entire thing being out for public review using the normal process as opposed to the Tiger process. And in terms of the residential, 62.2 has a task group that's considering whether it wants to write an appendix, which will be essentially the 241 for residential as an optional appendix in 62.2. So that's just in exploration. I don't know what the committee will decide to do, but they've decided to explore the issue.
We covered an immense amount of amazing topics, and I just want to say I'm so grateful for your generosity to share all this stuff, and thanks for all the good work you do.
Okay.